colegas, muchísimas gracias por conectarse a esta nueva edición del Seminario de Investigación del MODEMAT. I will switch to English now. Today we have Matteo Focardi with us. Thank you, Matteo, for accepting our invitation to give this talk. Matteo, as you know, is professor in the University of Florence in Italy. And of course, he has visited us 2 years ago, I think, right? Or 3 years ago in Quito.
2018.
Okay, cool. And now we have Matteo again with us, at least virtually, back to Quito. So thank you, Matteo, again for accepting, and the audience is yours.
Thank you very much. And of course, many thanks, Sergio, for your invitation. And I wish to say hello to everybody that I know in Quito. It was really a pleasure to be there. And I'm happy to share with you some results that I obtained recently with Camillo De Lellis from the Institute of Advanced Studies in Princeton, and Silvia Ghinassi, who was a postdoc there last summer, but then she moved to Washington University. And these results are about the Mumford-Shah functionals, more precisely on the regularity of the singular sets of minimizers. But rather than going directly to our results, I will make a very long survey of the existing regularity theory. So I will start really from the problem as it was stated by Mumford-Shah in 1989, and then I will go through, and at the very end of through the regularity theory, and at the very end of the talk I will show you our new insights on the problem. Okay, so the Mumford-Shah problem was introduced in 1989 as a model for image segmentation and edge detection. So it's a two-dimensional model. That is why I will always stick to 2 dimensions, even though many of the results that I'm going to state have higher dimensional analogs. Not all of them, but many. And essentially, the model is introduced because you have a black and white picture, which is represented by this function g here. So say that 0 is black and 1 is white. And the objects in the picture, which is represented by a omega, which is a rectangle, are somehow represented by the level of grays. So G is giving you the level of grays of the objects in the picture. And you have some noise. And Mumford-Shah proposed a way to find a denoised version, a deblurred version of the image G, together with somehow the finding of the edges of the objects in the picture. So the model is a variational model, so you have to minimize an energy on couples U and K. So essentially the energy is the sum of 3 terms. Let me start from the third one, which is called the fidelity term, and which is the square L2 distance of U from G. So essentially, the fidelity term is there because you want that the output of the model is in some sense close to the input. So you want that this quantity is not too large. But the most relevant part of the energy is actually hidden in what I call the E of U and K, which is the sum of bulk energy and of length term. So essentially, K represents the set of contours of the object in your image. And the fact that you're penalizing the length of the contours is there because you want to somehow avoid an over-segmentation problem. That is, adding fake contours would, if you would not penalize this term here, may be helpful to decrease the energy. So you don't want this phenomenon, so you want to penalize the H1 measure of K, the length of K. So K, say it's a compact subset of omega bar. And the bulk term instead is the Dirichlet energy of U outside K. So say that U is a smooth function outside the K, and this term here is present because you want sharp transitions from black to white. You don't want to go from black to white with a thin layer of grays. You want to be preferable that you jump from black to white with a very sharp transition. And somehow, this is a prototype problem nowadays of what De Giorgi called the free discontinuity problem. And this kind of energies has found, with of course suitable modification, has found a lot of applications also in fracture mechanics, essentially in Griffith brittle theory of fracture mechanics, or also for Barenblatt cohesive models, and many others actual applications. So let me then tell you that you have a variational model. Of course, the first step is to prove existence of minimizers. And the problem that you face from the very beginning is the difficulty in finding a topology which is giving you at the same time compactness and lower semi-continuity. And the problem is essentially because of this term here. So there are very classical examples that tells you that, for instance, the natural topology would be that of a Hausdorff convergence of closed sets, but this term is not lower semi-continuous. So as far as I know, there are two approaches to deal with this problem. The first one has been proposed by De Giorgi Ambrosio, and from that paper in 1998 started all the theory of special functions with bounded variation. Essentially, you find a weak formulation of the problem, you prove existence of weak minimizer, and then you prove via some mild regularity theorem that the weak minimizer is actually a strong minimizer as well. And there is also another approach, which was started by Dalmaso, Morel, and Solimini in 2 dimensions, but not fully developed. It was then fully developed later on by Maddalena and Solimini, in which you prove that you can build some minimizing sequences with the corresponding set K more regular, satisfying a more regular, they are more regular than expected, essentially. Let me tell you that the kind of regularity that I'm referring to is very mild. For instance, this is the one that you get from the Giorgi and Ambrosio approach, which is called in literature Alford's regularity. And this means that if you pick any ball centered in a point of the jump set K, and you look at the amount of length of K inside this ball, this is always proportional to the radius of the ball. So the estimate from above is quite simple. You get it by a direct comparison with a suitable test function. What is very hard is what is called the density lower bound. And this is obtained, has been obtained by De Giorgi, Carrière, and Leache in this seminal contribution. For instance, a consequence of these Alford's regularity properties that you do not have isolated points in the set K. This is forbidden by this kind of regularity. And this property actually will be crucial also for a higher regularity purposes, as I will tell you later on. So for me, existence is now given for granted after these contributions by all these authors. And of course, once you have existence, what you are really interested into is the regularity of both U and K. And in order to do this, I do what is usual in regularity theory. I make some blow up, a sort of a rescaling argument. This means that you take a ball B rho X and you translate and dilate it to the unit ball. In the independent variable, you do this homotopy, this dilation here. This corresponds in the set K to consider the set K rho defined here. But if you remember, in the energy E, there was a bulk term, a volume term, and a length term. And they behave differently for what rescalings are concerned. So in order to balance them, you have to multiply U by this prefactor here in front, rho to the power -1/2. And then you try to, in some sense, Taylor expand the energy with respect to rho. And this is what you find out. So if you write the energy, the full energy of an admissible couple UK, and you divide by rho, what you find out is that this energy is equal to the energy E of the couple U rho K rho in the ball B1 plus rho squared, the square L2 difference of U rho from G rho. And let me analyze the order of all these terms. So this first summoned here, if we go back to this Alford's regularity property, is of order 1, at least for what the length term is concerned, but you can prove a similar estimate also for the gradient. So this term here is of order 1, while this term here is of order rho, because say G is in L infinity, so G rho is of order rho to the minus 1/2. For what minimizing sequences and minimizers are concerned, actually, somehow it's enough. You have maximum principle, which is telling you that it's enough to consider functions which are in L infinity with the same L infinity bound of G. So U rho minus G rho is of order rho to the minus 1/2. And so its L2 norm is of order rho to the minus 1. You are multiplying by rho squared. So this is of order rho. So what this actually computation is telling you is that the fidelity term is a higher order for rho very small. And this is why from now on, I will neglect the fidelity term, and I will consider what in literature are called local minimizers of the energy, meaning that UK minimizes the sum of the bulk term and the length term among all compactly supported perturbation. Somehow, once you understand the regularity for local minimizers, you can prove similar results in a perturbative way for minimizers of the full energy. So this is more or less the principle. So I will consider only minimizers from now on of the energy E. And of course, we have necessary conditions. So we would like to figure out some explicit examples of local minimizers. So we have necessary conditions which are given by Euler-Lagrange equations. We have actually two families of Euler-Lagrange equations. So the first one corresponds to what I call outer variations. These are simply obtained by summing to U epsilon phi, and then you you expand in epsilon and you impose the minimality condition and you get this kind of equality here. But there are also some other variations that you can take, which are called inner variations, and they are obtained essentially by moving omega via diffeomorphism. So with the outer variation, you are fixing the set K. So K is unchanged when you take the outer variation because you only move the function U. While with the inner variation, you use a diffeomorphism which moves also K, and you get this kind of equality here. I don't want to read this equality. What I want to tell you is what are the consequences in case you assume that K is smooth enough, say C1. So if K is, say, a smooth curve inside a subset A of omega, what you can prove is that from the outer variation, you get that U is harmonic out of K, and it satisfies some Neumann boundary conditions on K. So U is as smooth as you want because it satisfies this system here, provided that you know that K is a smooth curve. And the inner variation is giving you a link between the two unknown of the problem, K and U, because the inner variation implies that after some integration by parts, that the curvature of K inside A can be written in terms of the jump of the square of the gradient of U through the interface. So you prove that the gradient has some traces on K, if K is smooth enough. It jumps across this interface K, and the curvature of K can be written as the difference of the traces of the gradient from the two sides of K. So it's a really important piece of information. So you get some PDEs with which you can study the regularity of K itself, provided that you know that K is a smooth curve. And this is what we are going to try to understand in what follows. So, but for the time being, let me tell you that once you have Euler-Lagrange equation, you can find candidates for examples of local minimizers. And somehow, some people, especially Alberti, Buscitte, and Almaso, found a way to prove that some of these candidates are actually true local minimizers of the Mumford-Shah energy. So they establish what is called the calibration theory. So they are a way to prove that some critical points are actually local minimizers of the energy. And the list of critical points is here. So you have the trivial somehow couple, which is given by an harmonic function u and for k the empty set. The pure jump configuration, meaning that k is a line and then u is a piecewise constant function, which the constants change when you cross the line. And then we have also the so-called triple junction configuration. Again, u is locally constant. And the set k is what is called the propeller. That is, it's the union of three half lines. They have the end point in common, and the angles at the end point are equal. So 2/3 pi. And what Alberti, Bouchette, and Dalmaso proved is that if, say, omega is a ball, and the radius of the ball is sufficiently small, then actually these three examples here are indeed local minimizers of the energy. And what I want to stress is that R has to be sufficiently small. Indeed, if R is big enough, they are no longer, they are critical points, but they are no longer local minimizers. And they are not even what I call global, then they are not even global minimizers. That is, they do not minimize the energy on every bounded open subset of omega, right? So you take of R2, sorry. So you take any bounded open subset A, you take compact perturbation of u and k inside A, and you impose this kind of minimality condition for every A. So these three couples here do not satisfy this kind of condition, which is global minimality. And here comes the first conjecture of the theory, which was stated by De Giorgi. So De Giorgi in 1991 conjectured that the only non-constant global minimizer of the Mumford-Shah energy is the so-called crack tip function. So uniqueness has to be understood up to translation, rotation, and addition of constants. So by crack tip function, I mean the real part of the complex square root, which has to be pre-multiplied by this factor here. So 2 over pi, square root of 2 over pi. So this factor here comes from the inner variation. So if you take any multiple of the real part of the complex square root, you realize that to satisfy the inner variation condition, the prefactor has to be 2 over pi, the square root of 2 over pi. And the jump set here is the positive reals. So somehow, so here I have depicted the jump set for the crack tip configuration. And let me tell you that half of this conjecture has been proven by Bonnet and David, who proved that actually the crack tip is a global minimizer. The issue of uniqueness is still open, and it's very important, as we will see. Indeed, somehow this conjecture by De Giorgi is related to what is the Mumford-Shah conjecture. The Mumford-Shah conjecture is about the structure of the set K. So according to Mumford-Shah, the set K of a local minimizer is a locally finite union of C1 arcs, injective arcs, C1 up to the ends, so on the full interval AI, BI. So the union is locally finite, and only a few configurations can occur. Either you have a loose end, or if two arcs are meeting, they meet in an endpoint, and actually there is a third arc meeting there, and the angle in the endpoint are all equal, so 2/3 pi. So essentially, the configurations are the one that we have in mind via these examples here. Only this configuration can occur, at least infinitesimally. And indeed, what somehow the Mumford-Shah conjecture is telling you is that if you take a point of if it's true, if it were true, somehow if you take a point of K and a little ball around this point, either the set K is close to a diameter if you are inside one of these arcs, or is very close to a radius if you are at the tip of an arc, or if you are in a center of a propeller, you are very close to a propeller itself. And what regularity theory is doing for you is that is proving a converse of this statement in some sense. It's telling you that if K is close in a suitable sense to one of these three configurations, then K is smooth. This is what regularity is going to do for us. So let me start with the first regularity result, which is due to Bonnet, who proved actually that the Mumford-Shah conjecture in a weak form is actually true for the isolated connected components of K. So what I mean with weak form I mean that the regularity of the arc is in the interior. So the endpoints are not considered. So for instance, the Bonnet result doesn't forbid this kind of second configuration that I've depicted here. That is that the fact that the arc may spiral around the endpoint. So this is a C1 arc in the interior, but none up to the tip. And of course, somehow this is a nice achievement, of course. And actually somehow what you really can prove out of Bonnet argument is that if you have a bound on the number of connected components of the minimizer, that is, if you knew a priori that K has only a finite number of connected components, then you could prove the weak form of the Mumford-Shah conjecture. But this bound is not available a priori, so still the conjecture is open. Let me tell you something more about the Bonnet approach. So the Bonnet approach passes through a weaker notion of minimality, which nowadays is called Bonnet minimizers. So apart from the fact that UK must minimize the energy up to compact perturbation, there is a topological condition that he added, and which prevents the fact that I mentioned before, that for instance, for large radii, the triple junction configuration, the pure junction configuration, and the harmonic configurations are no longer a local minimizer. So this topological condition is avoiding that phenomenon. So he has a weaker notion of minimizers, because what he can prove is that the problem has some compactness. That is, if you remember the couples U rho, K rho that I introduced some slides ago, they converge in a suitable sense to a couple U0, K0. This is a global Bonnet minimizer, so it minimizes the energy according to the definition that I wrote in the previous slide. On the full R2, here I wrote the kind of compactness that it's encoded in the problem, but it's not important. And what it's really important is that if Bonnet assumes that K0 is connected, then he's able to classify all possible global Bonnet minimizer. That is, if K0 is connected, then U0, K0 either is the harmonic configuration, or the pure jump configuration, or the triple junction configuration, or the crack tip configuration. So the list is finite, and once he knows that the list is finite, he can prove the regularity. And indeed, as I told you, if somehow you can rephrase Bonnet contribution saying that if you knew that all global Bonnet minimizer belong to the list that I just told you, then the weak form of the Mumford-Shah conjecture is true. And that is why people started to try to classify all possible global Bonnet minimizer. And here I want to state another contribution by David and Leger, who proved that if you have a global Bonnet minimizer for which K is neither a line nor a propeller, then necessarily the complement of K is connected. So you can rephrase this contribution as follows. That is, if R2 minus K is not connected, then necessarily K is either a line or a propeller. So essentially what I call an exotic global minimizer, meaning that it doesn't belong to the list here, either has to, so the set K must be not connected, because the result of Bonnet tells you what are the global minimizer in if K is connected, and R2 minus K has to be connected, because otherwise the result by David and Leger tells you that K is either a line or a propeller. So we don't know if exotic global Bonnet minimizer exists. But what is important of this contribution by David and Leger is that since R2 minus K is connected, somehow the topological condition in the global Bonnet minimality is trivialized. So it's completely equivalent to global minimality in our sense, that is, you have to minimize the energy up to compactly supported perturbation. And so essentially, if you're able to prove the uniqueness part of the De Giorgi conjecture, that is that the crack tip is the only global minimizer, you would have proven directly the weak form of the Mumford-Shah conjecture, putting all together this contribution. So essentially, what I wanted to convey with this approach is that we have a strategy to attack the Mumford-Shah conjecture, even though we are not able to implement this strategy. So this is somehow one way to deal with the conjecture. In the next slides, I will actually tell you another way, which are more accustomed with, and everything starts with this contribution by Ambrosio, Fusco, and Pallare in '97, who proved an epsilon regularity result. In the spirit of the regularity theory of minimal surfaces, what they proved is the following. So if you're given a local minimizer of the Mumford-Shah energy, you can find a subset sigma in K, which from now on I will call the singular set. So there is a set sigma, which is relatively closed in omega, in K, which is H1 null, and outside of sigma, K is C1. Then somehow, once you know that it's a C1 graph, the inner variation, the condition on the curvature that I wrote you is telling that for free is C11. But what is most relevant in the contribution by Ambrosio, Fusco, and Pallare is that you can describe sigma via an epsilon regularity criterion. That is, a sigma is the subset of points in K for which a certain quantity has to be above a threshold epsilon. What is this quantity? So this quantity is the sum of the scale Dirichlet energy. So you take the Dirichlet energy of U in the ball B rho x, and then you pre-multiply by this factor here. And this is because this quantity is scaling invariant. It means that if you change variables, you get the Dirichlet energy of the function U rho that I wrote before on the ball B1. And the second quantity is so-called scaled mean flatness, or B2 Peter-Jones number. So somehow it's an integral way to measure how a set is flat. So what you do is the following. You take K intersected B rho x. You take the square distance of every point in this set here from a line. You integrate over K intersected B rho x, and then you minimize on all possible lines. And then again, you have to pre-multiply by a factor in order to make the quantity scaling invariant. And again, if you change variables, what you get is the mean flatness of the set K rho in the ball B1. So it's an integral way which in the last years has gained a lot of popularity to understand rectifiability issues of sets. So what Ambrosio, Fusco, and Pallare proves is that in the points in the singular sets are points in which the sum of these two quantities has to be above a given threshold. So there is also another nice contribution in the same spirit by David, who in 2 dimensions, the result by Ambrosio, Fusco, and Pallare holds in any dimension. So in 2 dimensions, David proved an analogous result where the epsilon regularity criterion is given in terms of a different quantity. It's an L-infinity version of the scale L2 scale mean flatness, but somehow all these quantities are equivalent because of the Alford's regularity of K that I stated at the beginning. But what David in 2 dimensions proves more than Ambrosio, Fusco, and Pallare is that this set sigma is not only H1 null, but has a Hausdorff dimension strictly smaller than 1. Okay, I will come back to this later on. Let me now use the result by Ambrosio and Fusco and Pallare to make a comparison with the Mumford-Shah conjecture. So what I do is the following. I take the singular set and I split it into the union of 3 disjoint subsets. So the first set is the set of points for which, of singular points for which the scale Dirichlet energy is infinitesimal. So for sure, the scale mean flatness is not infinitesimal because these are singular points. And as an example, you might think of triple junctions configuration. So for the triple junction, the function is locally constant, so the Dirichlet energy is null, but of course this set propeller is not flat because in the center of the propeller you have 3 lines meeting there. And indeed, I will give also a justification for this name, sigma 1, as the set of triple junctions, because infinitesimally, what you see in points of this kind, you always see a triple junction. Then I have the set where the opposite occurs, meaning that the scaled mean flatness is going to 0, but not the scaled Dirichlet energy. And as an example, you might think of crack tips function, for which this is true because somehow the set K for a crack tip is a half line, so it's flat. So this is identically null, but the Dirichlet energy is constant. The scale Dirichlet energy is constant. And then you have the rest. And according to the Mumford-Shah conjecture, this set sigma 3 should be empty, but we do not know if this is true or not. So in what follows, I'll tell you in the last 20 years what we have understood about the set sigma 1 and sigma 2. So let me start with sigma 1, stating a very beautiful result by Ambrosio, Fusk, and Hutchinson, who proved that in 2 dimensions, actually the set sigma 1 has a 0 Hausdorff dimension. So it's a very, very small set. So we, together with Camillo and Berardo Ruffini, we gave a simplified proof of the statement. And actually in 2 dimensions, you can prove much more. You can prove that the set not only is of 0 Hausdorff dimension, is really countable via some topological argument, which holds only in 2 dimensions. And apart from the size of the set, let me justify the name of sigma 1 as the set of triple junctions. So there is a very beautiful epsilon regularity result by Guy David, who proves the following. So if you're given a local minimizer of the Mumford-Shah energy, and you know that in some ball BRZ, the scale Dirichlet energy and the scaled and infinity version of the mean flatness from a propeller C is sufficiently small, is smaller than a certain threshold epsilon, then what you know is that K in a slightly smaller ball comparable to the radius R, in which you're measuring the distance of K from the propeller C, is actually K in this slightly smaller ball is a diffeomorphic image of phi. So it's a very precise description of K inside this slightly smaller ball. So you really see 3 arcs, C1 arcs meeting in a common point, and the tangents are forming equal angles. So this is why you call the set sigma 1 set of triple junctions, because, okay, here I stated the David result in which you have the sum of these 2 quantities to prove this result. But somehow by compactness, what you can prove is that you can get rid of this second summand here, and you can prove that if you are a singular point in which the scale Dirichlet energy is going to 0, so it's below a certain threshold, then you have this conclusion. So the name set of triple junctions come exactly because infinitesimally, in geometric measure theory, you would say in the blow-up limits, that is when you let rho go to 0, if you remember we had these couples u rho k rho, the limits of these sets of these couples u rho k rho are such that the set k rho are converging to a propeller, and u is converging to a locally constant function. This is the reason why you call the set sigma 1 the set of triple junctions. Okay, but let me tell you something more about this set sigma 1. So the next step by Ambrosio, Fusk, and Hutchinson in the same paper is to use this piece of information on the smallness of the set sigma 1 to prove the following result. If you are given a local minimizer for which the gradient enjoys a higher integrability property, it means that so the natural energy space for the gradient is L2. But if you know for some reason that the gradient is in LP for some p is bigger than 2 and less than 4, we will see why less than 4, then you could prove that the full singular set has Hausdorff dimension bounded by this number here, 2 minus pi p over 2. So p less than 4 comes from the fact that this number here has to be strictly bigger than 0, so p has to be less than 4. And of course, this number is strictly less than 1, and somehow it's a quantification of the result by Guy David. If you remember, I told you that David was proving that the singular set has Hausdorff dimension strictly less than 1, and this is a quantification in terms of the higher integrability exponent of the gradient. And some years later, together with Camillo, we proved that actually this assumption is always satisfied. So we proved that in 2 dimensions, the gradient of any local minimizer enjoys this high integrability property. And in 2 dimensions, we proved this result, and slightly later, Guido De Filippis and Alessio Figalli proved that this is true actually in any dimension. So the Mumford-Shah minimizers, their gradients always satisfy this higher integrability property, as it was conjectured by De Giorgi. And let me tell you that if you were able to push this exponent p up to 4, of course you would have that the Hausdorff dimension of sigma would be 0, which is not the Mumford-Shah conjecture, but it would tell you that the singular set is very, very small. So the better the higher integrability, the bigger the higher integrability exponent is, the smaller the singular set is. So let me make another step in this direction. So why p has to be less than 4? There is also another reason, not only because this number has to be bigger than 0, because there is an explicit example, which is the crack tip, which is telling you that its gradient is in LP for every p less than 4, but it's not in L4. So there is an explicit example which is telling you that L4 you can never expect. But actually, if you look more if you look closer to this example, you see that the gradient of the crack tip has a very sharp higher integrability property in the scale of weak Lebesgue spaces, better than not L4, but much better than every LP. And what we realized with Camillo that actually this is giving you an energetic way to characterize the Mumford-Shah conjecture, or at least its weak form. That is that the arcs are C1 in their interior, not up to the ends. So what we proved using Bonnets regularity theory is that the Mumford-Shah conjecture in the weak form for a local minimizer is equivalent to proving that the gradient is in L4 infinity, meaning that the super level sets of the gradient decay like the negative power of somehow the lambda super level set decay like the negative 4 power of lambda. So this is another way, another approach to somehow attack the conjecture, even though it's still purely academic because we don't know how to prove this, and we don't know even how big this exponent is in both the proofs of Alessio and Guido and Camillo and myself. So we know that there is an exponent. Maybe we can quantify it slightly bigger than 2, but we don't know how to improve it better and better. So it's still a purely academic path to be followed. So, and with this, I'm done with the set sigma 1 and all with the survey of the what is known. Let me come back to the more recent results, and they are concerned with the set sigma 2, which, if you remember, I called the set of crack tips point. So the set sigma 2 is the set of points where the scale mean flatness is going to 0. But of course, since these are singular points, the scale Dirichlet energy is not. And as a prototype example, I told you to think about the crack tip configuration, which has as a jump set exactly a half line, but the scale Dirichlet energy is constantly equal to 1. And to justify the name for the set sigma 2 as the set of crack tip points, I'm quoting again a very beautiful result by Guy David, which is again in the spirit of epsilon regularity. So what David proved is the following. So if you're given a local minimizer of the energy, and you know that in some ball BRZ, the set K is close to a radius of the ball, close in the sense that if you take the Hausdorff distance of K inside this ball from this radius and you scale it by R, this is below a certain threshold, then what David proves is that essentially the set K is a single, is a connected smooth arc. So more precisely what he can find is a point Y naught and a smooth parameterization gamma in a way that in a ball of comparable radius, say BR over 2Z, K is parameterized by Y naught plus rho cos gamma sin gamma. And then he has some estimates on the tangent vector of on the velocity of the parameterizations. So the epsilon regularity result by David is telling you that if you are very close to a radius of the in a ball, if you are very close to a radius, then you are a single connected smooth arc. But again, if you look closer at the result by David, somehow he's not somehow ruling out this second possibility here. The fact that the arc is spiraling around the tip. So for instance, if you take gamma of rho as the logarithm of the absolute value of the logarithm of rho, this is consistent with David result. And this is not nice also in view of application for the Mumford-Shah model in image segmentation. This is something that you wouldn't like at all. So this is what we tried to figure out with Camillo some years ago. So, and this is the result. Actually, somehow there is a long story behind this result. So we gave a proof in 2015, which actually contained a gap. Then also Anderson and Michaelian about 1 year later gave a proof, but also their proof contained a gap, and then they came out with a different argument. And we got interested into this problem last summer together with Silvia, and then we found a way to close the gap in our proof, and this is what we finally came up with. So essentially, we are under the assumption of the result by David. So we have that the set K is a connected smooth arc. And what we can prove is actually that it's not only a connected smooth arc, we can also prove that actually is the graph of a C2 alpha function in a ball of comparable radius. So K intersected this ball is the graph of a C2 alpha function, which has a second derivative null in the origin, that is at the tip. So essentially what I'm telling you is that this second behavior is not possible. So what you really see at small scale around the tip is this kind of behavior. So in the language of geometric measure theory, what we would have proven is that the uniqueness of the blow-up limit, that is of the limits of the couples U rho, K rho that I was telling you before. Because if this second behavior is allowed, if you take different sequences, what you can prove is that in the limit you can have you will always have crack tips, but the jump set can be either a line like this, or a line like this, or a half line like this, or a half line like this, or a half line in another direction. Instead, what we prove, since this behavior is not allowed, is that you always see one and only one crack tip in the blow-up limit. So it's a problem of uniqueness of the blow-up limit, with which you get this extra regularity on the set K. So K is C2 alpha up to the tip. And you know that indeed the curvature is vanishing. Let me tell you that somehow the argument with Camillo and Silvia, contrary to that of Anderson and Michaelian, is also able to deal with critical points of the Mumford-Shah energy, not only minimizers, local minimizers. With critical points, I mean couples U and K, which satisfies both the outer variation and the inner variation system. But of course, in this case, we have to assume that we are under the conclusion of David results. That is, we know that K around it's a single connected smooth arc, because now David regularity theory is not available, at least so far, for critical points. Under these assumptions, we are able to prove the same results, that here I wrote in a slightly different fashion. So I'm writing that the curvature is decreasing in the tip as a power of the radius, of the distance from the tip. So the fact that we are able to deal with critical points is because somehow the main ingredients that we found, at least the main new ingredient that we found to close the gap, is related again to the inner variation. So there are a lot of ingredients dealing with linearization of the outer variation system and the inner variation system. I don't want to enter into the proofs because they are very technical, but I want to state the new main ingredient that we had, which is what we call singular inner variation. So if you think more or less, it was one of the first slides of the talk. I wrote a necessary condition for the local minimizer, which is the first line written here equal to 0. This corresponds exactly to the equation that I written here when eta is compactly supported. And indeed, the inner variation was somehow valid only for compactly supported fields eta. So what we wanted to take is eta not compactly supported, and you can do it actually in a very elementary way by some approximation argument, in a way that somehow what you get is on the right hand side, rather than 0, when eta is not compactly supported, you get some boundary integrals, which are really important for us to close our argument. So it's somehow what we were missing before is that we were taking of the inner variation of the inner variations, we were only taking, if you remember, I wrote that from the inner variation you can write an equation for the curvature. So we were considering only the equation of the curvature. Instead, the inner variation is equation is much richer, and indeed somehow we are able to get some other piece of information from this new family of that we call singular inner variations. So this family is new in the sense that there was only one instance in literature known. And this goes back again to another result that I quoted, the one by David and Leger when I was talking about the Bonnet, the problem of Bonnet, of the classification of global Bonnet minimizer. So David and Leger and independently Maddalena and Solimini at some point wrote down a formula to prove some monotonicity formulas that were an essential step in the proof of the classification of global Bonnet minimizers when R2 minus K was not is not connected, which corresponds to our inner variation in case the field eta of x is the identity. So they get in 2 dimensions this strange formula. And what we realize is actually that you can take much more general fields. And from this, somehow we are able, from these pieces of information, we are able to finally implement the strategy that we had in our first proof with Camillo. So I don't want to enter into the technicalities, but somehow this is also why we are able to deal with critical points, because these kind of singular inner variations are true for critical points, that is for couples U and K which satisfy the inner variation equation. Okay, so let me conclude by resuming what we have seen in this long survey. So essentially we have seen 2 approaches to deal with the Mumford-Shah conjecture. So the Mumford-Shah conjecture is giving you a very precise statement on the structure of the jump set of the set K in a local minimizer. So you remember that K for the Mumford-Shah conjecture is a locally finite union of C1 arcs up to the tips, the end of the arcs, that either you have a loose end, or if 2 arcs are meeting, they are meeting in an endpoint, and actually then there are 3 arcs meeting there with equal angles. So one way to attack the conjecture, as we have seen, started with the work of Bonnet, is to classify all global Bonnet minimizer. That is to prove that all possible global Bonnet minimizers are given by the harmonic, let me say, configuration, that is U is the constant function and the set K is empty, or the pure jump configuration, that is K is a straight line and U is a piecewise constant, that is constant in the complement, or a triple junction configuration. So K is a propeller, the union of 3 half lines meeting in a common point with the equal angles, and U how in the complement of the propeller is constant, piecewise constant, sorry, or a crack tip configuration, that is a multiple, a specific multiple of the real part of the complex square root. So if you are able to prove that all global Bonnet minimizer belong to this list, then you are able to prove the Mumford-Shah conjecture. Now, in the full somehow in its full statement, because now with this result by Anderson, Michaelian, Camillo, Silvia, and myself, you are able to prove that the arcs are smooth up to the tips, essentially. And this classification issue is actually related to another conjecture by De Giorgi, to the uniqueness issue in De Giorgi's conjecture, as we have seen by the work of Bonnets and David and Leger. If you're able to prove that the only non-constant global minimizer is the crack tip function, then you get the classification and the Mumford-Shah conjecture. So this is the first possible strategy to attack the Mumford-Shah conjecture. But then there is also another strategy, which is related to the higher integrability properties of the gradient of a local minimizer. So if you're able to prove that the gradient satisfies this higher integrability property in the scale of weak Lebesgue spaces, then you are able to prove again the strong form of the Mumford-Shah conjecture. And let me conclude this talk by saying that even though, of course, nowadays the Mumford-Shah model probably is no longer the most fancy model in image reconstruction and edge detection, still it has had a tremendous impact in many other fields, and a lot of mathematics has been done studying this problem, and still there are in different fields, and still it's a very rich of also maybe not only you, of course, you would like to prove the Mumford-Shah conjecture, but even though you are not able to prove it and you are able to prove some side results, you're still very happy. It's a very interesting problem. So with this, I think I'm done, and I thank you all for your attention.
Thank you, Matteo. It was a very, very interesting talk. And well, time for questions or comments. So, Matteo, I have one, but
yes,
probably it's very, very basic. As far as I understand, the idea is to have a description or a characterization for K, right? This is more or less the intention of improving regularity. But is it possible to do that? I mean, in some cases, because for instance, in elasticity, which I am a little more familiar with, usually this is the big problem, is to characterize the form of the way in which the fracture behaves. So how possible is to do it from this perspective?
So, I mean, of course, we are always talking about qualitative features of the set K. So there are some explicit examples, for instance, the one that I wrote down at the beginning, but there are not many others in which you are able really to say explicitly what are local minimizers of the energy. So also many examples are, we have not plenty of examples. So what you're really trying to say is that whatever the minimizer is, you're trying to say that not many phenomena can occur. Okay. And this is precisely what the Mumford-Shah conjecture is telling you, that at least qualitatively, you know that the set K is a locally finite union of smooth arcs.
Yeah, of course.
And they can either have loose ends or they join in this specific way. This is what you want to say qualitatively. Then, of course, somehow in some more explicit example, you would like to say something more. For instance, when I was talking about the triple junction configuration, it's not clear that if you impose somehow that this is indeed a local minimizer of the energy. Okay, so you know that maybe you put some boundary condition, but you don't know if this is the best way for the energy this is the way to minimize the energy.
Okay. Also some in the same sense, I mean, curiosity more than actually a question. These problems usually are also analyzed from the non-local perspective. So Is there a similar problem, or there is a version of the problem from this perspective of locality or something like that?
This I really don't know. If you can allow for discontinuities having somehow having length discontinuities with a non-local functional. This is something that I really don't know.
Okay. Thank you, Matteo. So, do we have more questions or comments?
I have a small one. Probably it's kind of naive, but
David.
I don't know how if you have heard about the Mumford-Shah model that uses a different operator different than the gradient. Because in your last slide you were assuming regularity property for the gradient, right? In order to comply with Mumford-Shah.
So you mean about the higher integrability? Yes.
Correct.
So what kind of operator are you thinking about?
I mean, I was thinking about, let's say, this one looks like a TB, let's say, a total variation kind of. Because
but this changes a lot.
When you use a second order, for instance, let's say you use a different
but this changes a lot. So somehow, for instance,
lot, right?
The higher integrability, as far as I know, is known, of course, for the Mumford-Shah functional, but also for when the square gradient is substituted by, I don't know, the quadratic form with suitable smoothness of the coefficients. But with more general, also in that case, with more general functionals, I don't know if it's true or not. And second order is, I would say, much harder.
Yeah, I could imagine that.
The first result, the epsilon regularity result by Ambrosio, Fusco, and Pallara, I don't know if it's known in that setting as well or not. This is, I think, is missing. Or at least if you think about the symmetrized gradient, which is something that appears also in models for linearized in fracture mechanics for some linearized models, it's not known that kind of result. There is something if you assume that you have one case made up of one connected components, then you know that is up to a set with H1 null, then it's locally a C11 arc, which is the starting point for the regularity of K. So there are some results in different contexts, but somehow at least to get a way to prove a sort of a similar structural, at least to imagine a similar structural behavior for the set K with different energies, we still miss the basic regularity results, actually, I would say.
That's great. Thank you very much for the talk. It was really interesting.
Thank you. Thank you very much for your attention. Thank you.
I have another naive question.
Yes, please.
From the practical point of view, sometimes there is a regularization to make some computations of the Mumford-Shah functional. I wonder if there is possible, or there have been some work related to the convergence to B minimizers of these solutions for the regularized problems?
So with regularized, what do you mean? For instance, phase field approximation or?
Yes, any kind of regularization. I mean, if it is possible to see if the regularized minimizer can converge to the B minimizers.
I think that whenever you prove, for instance, the Ambrosio-Tortorelli approximation of the Mumford-Shah energy, you prove some kind of convergence for every minimizer of your energy, global minimizer though. So this is an issue, even though I think that there are some results by Frankfurt, Serfati, and another author that I don't remember, also valid for local minimizers. You can prove that you can approximate with minimizers, local or global, depending on the context, of the regularized problem. The fact is that I don't think that the regularity estimates are passing to the limit. You have some kind of very weak convergence statement. For instance, you have convergence in the sense of Hausdorff convergence for Setzer and W12 outside of K, a neighborhood of K for the fields, for the corresponding fields, but you do not have strong enough convergences for the regularity estimates.
Okay, thank you. Thank you for
You're
the
welcome.
presentation.
Thank you. You have the no audio, Sergio. We don't hear you.
Sorry. Sorry. Do we have more questions or comments? Okay, not being the case. Matteo, thank you again for this very interesting talk. Also for accepting our invitation and being part of this seminar.
It's always a pleasure.
I hope that in the near future we can meet again. I mean, finger crossed. Well, thank you again. Gracias, colegas, por su participación, por haberse conectado. Y creo que todos estamos gratos con Mateo.
Thank you to all of you, and thank you again. Bye.
Gracias, Mateo.
Que les vaya muy bien.
Bye to all
Una
of you.
buena tarde. Adiós.
Ciao.
Bye. Cuídense.
Ciao. Ciao. Oh, ciao Marco.